Hello there, welcome back to my channel. Thanks for clicking on yet another video that really means a lot to me. Now, this is where we break down artificial intelligence, the huge jargons as to what AI is, what does it comprise of, into simplified yet understandable manner. So once you watch all of my videos which are already live and which are yet to come out, you are gonna be this pro in AI so that you can succeed in your career and become this AI master out there. So before we begin, let me introduce myself. I'm Aarti, a data scientist. I've been a data scientist for over 6 years now, but I am not from a technical background. That's what I keep saying. So I have a bachelor's in biotechnology and a master's in biostatistics and epidemiology. But somewhere in between I got into AI. But it wasn't really, the beautiful paradise that you can imagine. I had a lot of rough starts and a lot of failures. I even cried a couple of days. Let's not get into it right now. But I did overcome all of those, and the kind of programming that I do today, would have never imagined it in my bachelor's, or let's say even in my master's. So with that being said, let's dive into the video today, shall we? So today we're going to look at different machine learning algorithms out there. So in one of our previous videos, we would have spoken about what are the different types of learning algorithms out there. Alright, so imagine machine learning algorithms as your toolbox, you know what I mean. So this whole toolbox has 3 main drawers, and each of these drawers is your different types of algorithms that you can group into different categories. Now you have one drawer which is a supervised learning algorithm, and then the other drawer is an unsupervised learning algorithm. The third one is the reinforcement learning algorithm. So, when we open each of these drawers, you find huge and various types of algorithms within it. So let's dissect one by one. Under supervised, you have something called a classification and a regression model. Under unsupervised, you have clustering and then dimensionality detection. Under reinforcement, there are a lot of different models out there. So just to recap what a supervised, unsupervised and reinforcement is. Supervised is when you have a labeled data set, you have a set of instructions that your model can follow in getting its desired output. Unsupervised is when labeling is very expensive. You do not have a labeled set of data with you yet. So you just give the raw data as an input to your model, and your model understands the pattern within it and gives you the required output. Reinforcement learning is similar to how you train your dog. So the model first prints you an output, and then depending on how the output is, you either reward the model or you kind of give a penalty. So if the output is what you have expected, you give a reward function, so the model learns back understanding that this is the kind of output the user wants. If the model prints out a very bad output, you give a penalty function, which the model takes it in and then optimizes the output for our desired output. So that's reinforcement learning. Now let's get into each and every algorithm within every bucket over here. I'll give you a quick explainer as to what the algorithm is and give you a simple analogy that will help you remember it pretty well. So let's get into each of these different algorithms here. Okay, let's start with classification. This is when the machine has to put things into categories like spam or not spam, ripe or unripe, yes or no. Think of it like a chef decoding dessert or main course. So the algorithms that assign labels to data based on its learning patterns. So it is like sorting dishes into different categories, especially spam filtering, medical diagnosis and so on. There are a couple of different methods as to how you can do a classification model. So first up is the very famous Logistic Regression, my personal favorite. So it might sound very fancy, but it's just drawing a curve and then saying, yes or no answers. Like, is this dish spicy or not? If it's like a simple boundary that you draw, it's a binary classification model for which the answer is either an yes or a no. It's a cat or a dog. So things like that. Where do you use the specific logistic regression model? In classifying your emails, if it's spam or not a spam. Simple. Next up is the k nearest neighbors. So in KNN, k nearest neighbor, when you give it a new data point, it looks around its k nearest neighbors, which is like closest points, and decides its label based on what most of them are. In simpler words, show me what my neighbors are, I'll copy them. Imagine a data point saying that. So you're a new chef and you're trying to identify what you just cooked. I mean, you've cooked it, but you have no idea what it is. So you're not sure if it's a soup or if it's a biryani. You're just new at this. So you walk around, you ask your k nearest neighboring chefs. Say you have like 5 of them. If 3 out of 5 say that looks like a soup, then you call it a soup. That's literally how KNN works. It's majority voting among neighbors. It's a mini apartment out there with association and stuff. So in short, KNN is like when you're unsure about your dish, so you ask your nearby chefs. The majority decides what it is. The main use case for KNN is your handwriting recognition. Alright, next is the support vector machines or SVMs. Its goal is to separate classes of data like cats versus dogs, spam versus not spam, by drawing a boundary line in 2D plane, in higher dimensions. The key idea here is not just any boundary, but the one with the maximum margin, meaning the wildest possible gap between two classes. So it's like, imagine you're in the kitchen, sorting out your dishes. On the left, you have vegetarian dishes. On the right, you have non-vegetarian dishes. You want to draw a line on the table to separate them. Now, many lines could separate the two groups, but SVM picks the line that leaves the biggest safety margin, so there is maximum distance between the closest veg dish and the closest non-veg dish. This makes it less risky if a new dish is slightly ambiguous, like egg for instance. The margin gives it a cushion. So where do you use it in real life? In face recognition, email classification, medical diagnosis, whether the tumor is malignant or benign, and so on. In short, drawing the thickest possible dividing line between two classes, leaving the biggest buffer zone so mistakes are less likely. That's SVM for you. Next we have the decision trees. A decision tree is kind of like a flowchart model. So it asks a series of yes or no questions, we call it splits, until it reaches a final decision, which is the label. Each question is chosen so that it best separates the data at that particular step. Think of a recipe book. The first step would be, is the dish sweet? If the answer is yes, then go to the dessert section. If no, go to the main course section. Then inside the dessert section, you have is it baked? If yes, you go for cake. If no, you go for pudding. That's exactly how a decision tree works. At each branch, it splits based on one feature like sweetness, spiciness, temperature, and it follows the path down and you reach the final dish, which is your classification output. Where you actually use it in real life? Banks use it to decide loan approvals, questions like income, credit score, collateral, and so on. Doctors use it for diagnosis. You have fever, cough, do you test positive, and so on. E-commerce uses it for recommendation, like budget, product types, type, these are your features. So in short, decision trees are like recipe books. You start with a big question, then keep following the smaller questions until you land at the final dish. Next we have random forest. It's like an ensemble method. It takes a lot of decision trees, like the recipe book tree we just explained, and has each one make a prediction. Then it combines them, majority vote for classification or averaging for regression. The idea, it's like a group of weak trees together make much stronger, more reliable model. So a single decision tree is like following one recipe book out there. It might be biased or it can even make mistakes. But a forest of trees is like asking 100 recipe books what your dish is. Each gives its answer and the final decision is made by the majority vote. That way, one weird recipe won't throw you off. The crowd keeps it balanced. Where do we use it in real life? It's in fraud detection, where each tree looks at the transaction patterns, the forest decides if it's fraud. Medical diagnosis. Many trees analyze the patient data, the forest decides the risk. Recommendation systems. Multiple trees consider browsing history, the forest predicts the interest. In short, random forests, it's made up of a lot of decision trees working together and voting, so the final prediction is more accurate and less biased than a single tree. Next we have is the boosting algorithm, which is similar to random forest, but it comes with a twist. Instead of training all trees in parallel, it trains them sequentially. Each new tree tries to fix the mistakes of the previous ones. Over time, the model becomes stronger because every round focuses on the hardest to predict data. Imagine you have a team of chefs and each one is cooking one dish. The first chef makes it, but it's bland. The second chef tastes it and says, too salty in some parts, so they fix it. The third chef adjusts further, balancing the flavors. And after several iterations, chef after chef, the dish is far better than what the first chef made alone. They say too many cooks spoil the broth, but it's quite the opposite in this scenario. So that's how the boosting works. So every new chef, or the tree in this instance, improves on the weakness of the previous one. So where do we use it in real life? We use it for like predicting the customer churn, that is boosted models can catch subtle patterns that have been missed earlier. Credit scoring, it identifies risky customers better than one simple model out there. If you've never participated in a Kaggle competition, it works there as well. So XGBoost, LightGBM, CatBoost are all boosting techniques out there. So in short, boosting is models built one after another, each correcting the mistakes of the last, like chefs refining a dish until it's like very ultimate. Next we have the final classification model, the Naïve Bayes. It's a probabilistic classifier. It is based on a theorem called Bayes' theorem, which calculates probability of a class given some features. So the naive part here, it assumes that all features are independent of each other. In reality, that's rarely true, but the algorithm still performs surprisingly well in practice. So imagine a chef who's like tasting a dish. They assume that every ingredient adds flavor independently, which, if you think about it, it's sort of true. So for example, tomato makes your soup sour, chili makes it spicy, onion makes it kind of sweet. They doesn't consider that tomato plus onion together might change the flavor balance. They're being naive by ignoring interactions, but still most of the time their guess about the dish comes out correct. That's exactly what Naïve Bayes does. It treats each feature separately, multiplies the probabilities, and picks the most likely outcome. Where do we use it in real life? So email spam filtering. So here the keywords like lottery, free, win contribute independently. Sentiment analysis is another example where words like good, bad, excellent are treated independently. And then we have the text classification, so it categorizes news articles into politics, sports, tech, and so on. So in short, Naïve Bayes, the overconfident chef who assumes each ingredient works on its own, ignores interactions, but still often nails the dish. So we have learned a lot of machine learning models today.
We looked at the classification models under supervised learning. In the next video, we will look at regression models.
And we've even looked at a couple of examples and its real world use cases. And I really hope that it has given you a ray of hope that you are getting somewhere, you're at least like 10% into learning machine learning. So let me know what you think. And in the upcoming videos, we will get into each of these different algorithms and then dissect them into much more detailed form. We will also like implement a couple of them, and you would become a machine learning pro by the end of the series. So with that, ciao.